Hello engineering students, Mr. O again. Today I'm going to be doing the second example that I'm doing specifically on shear force and bending moment diagrams, and this is going to be class example 28.1, which you'll find in the Ivanhoe Ivanhoff book, textbook for mechanics and statics. You'll see it says on page 357. Okay, this is going to be shear force and bending moment diagram example. The question asks us, draw the shear force diagram and bending moment diagram for the simply supported beam below, including a force diagram in your answer. Oh, okay. So we haven't actually done a force diagram, but I'm going to redraw it anyway. And you'll notice, and I'm sure you can see this, they've actually given us the forces, the vertical forces. There are no axial loads, there are no angled loads. There's only 10 kilonewtons up and 8 kilonewtons up. They've given us the vertical supports for the fixed and the roller. Makes our life a lot easier and a lot simpler. So straight away I'm going to redraw this, just so they can make sure I know what I'm doing. There is a force. Let's do my force diagram now. 8 kilonewtons on the right, 10 kilonewtons on the left. And they seem to be all evenly spaced out. 2 meters, 2 meters, 2 meters, and 2 meters. And 8 kilonewtons, 6 and 4. So I'm going to go 8, 6, 4. 8 kilonewtons, 6 kilonewtons, and 4 kilonewtons. And I'm going to show you how to build the shear force and bending moment diagram. I've actually got an explanation here where I've drawn, I've actually laid it out. What I do is I first take these lines and I take them down in line with all the forces. If there was a UDL, you do it from the start of the UDL and the end of the UDL. These are all 2 meters apart. 2 meters, 2 meters, 2 meters, 2 meters. The whole beam is 8 meters long. Pretty well self-explanatory there. They've given us the forces on the left and the right. So all I'm going to do is draw my 0 axis for my shear force. And I'm going to draw my 0 for my bending moment diagram. And I'll start straight away. What I want to do is I want to work out what the shear force is at this point here. I'll call that number 1, a little circle, number 2, number 3, and number 4, just like I've done on this little diagram here. And that's going to be based there. What I then do is I really do a sum of the forces vertical in this. All my forces up will be positive, all my forces down will be negative, because the sum of my forces will equal 0. And we do that by going the sum of the forces downwards equals the sum of my forces upwards. I'll bring that over to this side, it becomes a negative, and my forces upwards stay positive. So that makes sense in that particular fashion. If I start with point 1, what I really do is I ignore everything to the right hand side of point 1. And all I've got is a force going upwards to 10. And I'm going to go up to 10 plus 10 kilonewtons. I take that across, and there's my shear force at number 1. Shear force at point 1 is 10 kilonewtons upwards. That's my plus. My next force, and I ignore everything to the right hand side, it's easier like that, of that point 2. But that's going to be up 10 and down 8. So shear force 2 point is plus 10 minus 8, which gives me plus 2. And I draw that on this diagram like that. If you look at it closely, it's really just following a 10 minus 8 will give me my point there, which is 2. I now move to the next one. And I ignore everything from 3, any forces on that beam to the right-hand side. This remains at plus 2. I'll take it diagonally across. And 3, my shear force at 3 up to that point is going to be plus 10, which is my 10 upwards, my 8 downwards, and my 6 downwards. That should become -4. It's not very hard, is it? I'll mark it there, and I go across to there. Making sense? I ignore everything else to the right-hand side. My shear force at 0.4 is going to be plus 10, minus 8, minus 6 because it's going down, minus 4 as well. So that's going to be minus 8. I go down an extra 4. And you can see it pretty simply. This is 8, my force downwards. This is 6, my force downwards. There to there is 4, my force downwards. So to maintain a balance, I double check it. I don't have a 0.5, but I work it out. I just call this a check, as if I go to the end point here. And that's going to be plus 10, minus 8, minus 6, minus 4, which we know ends up becoming minus 8. But I have an upwards force on my right being plus 8 is 0. And my shear force diagram, these are the shear forces that will be experienced along that span. There'll be 10, there'll be 2 between there and there, there'll be a -4 in the opposite direction, and then -8 across there and there. My maximum shear force being in the beginning part, which is going to be 10. Now I'll go down to my bending moment diagram. And just like I did my points 1, 2, and 3, and 4, I'm going to say bending moment diagram calcs. I forgot to do it up there. I'll write it now. Shear force. If the question does not give you the support, you got to quickly do a moment calculation and a vertical and horizontal vertical support calculation to work out what the supports are on either side. That should be very quick. I did in the previous question as well. In this case, they have given them to you, so it's a lot easier. And in this case, because I'm doing bending moments now, I look at each of the points. So I allocate a little diamond to that force, and a diamond to that force. That force becomes number 1. That force is number 0. That force is 3. That force is 4. And the last one, no, 1, 2, 3, 4. Let's look at force 0.0. I now do a moment at each of these points. And I start at the left and I ignore everything to the right. And I do a moment looking to the left only. If I do that, I have no distance. So straight away, my force bending moment 0 is force times distance. My distance is 0, is effectively 0. It would be 10 times 0. Again, sum of my moments of that whole beam should equal 0. Moments equals force times distance. Always put that in beforehand. And what this will also do is say that my clockwise moments will equals my counterclockwise moments equals my clockwise moments. I can bring that over to this side, and therefore clockwise moments are positive, counterclockwise moments are negative from the place that I'm doing the moment from. Let's go number 1. That point there, I cannot, there's no distance at all. At that point, I have no beam that's being used as a pivot point. There's no distance. So my force is 10 times 0 is 0. And I move to that point there. But ignoring everything to the right, I don't worry about that. I only look to the left. So from that point, if I have a little beam that's sitting there like that, it's only going to pivot that way by 2 meters. And so this is going to go clockwise. So my bending moment, so I start there and I do that one as 0. Bending moment 1 is force times distance. It's going to be positive because it's clockwise, 10 times 2. And that is 20 kilonewtons per meter. So at point 1, I now put 20 kilonewtons per meter. And I can draw a straight line to that. Now I go to diamond number 2. In other words, I move my pivot point from there and I move it to this side here and I ignore everything else. Therefore, I've got a little beam that's pivoting around that point there. Now I'm going to have 2 forces. I'm going to have this one going clockwise and this one causing my beam to go counterclockwise. Bending moment 2 is going to be clockwise, so clockwise is positive, plus 10 times, but from that point, it is 4 meters, minus the 8 times 2 meters from that pivot point. So what is that? That is 40 minus 16. This should be really simple to work out. 40 minus 16, 24 kilonewtons per meter. So at my point 2, I'm going to probably say it's about there. 24 kilonewtons per meter. I'm going to draw a straight line there. Point 3. I now move to diamond point number 3. So my beam pivots from there and I have 1 force going clockwise and 2 forces going counterclockwise. So bending moment 3 is 10 from there, 2, 4, 6, minus 8 by 2, no, 8 by 4. See how quickly you can make a mistake. 4 meters by 8 going counterclockwise, so 8 times 4 meters, minus 6 times 2. So what is my bending moment at point 3? I'll do this in the calculator here. It is going to be 10 times 6, 6, close brackets, minus, open brackets, 8 times 4, close brackets, minus, open brackets, 6 times 2, 16 kilonewtons per meter. So it drops off a little bit. I'd say down to about there. Now, if this beam is balanced and proving that our bending moments are also balanced, my clockwise moments equal my counterclockwise moments, my answer should end up being 0 at bending moment 4. So at this beam, at that point there, I'm going to have 3 forces going counterclockwise, that way anti-clockwise, and 1 going clockwise, but at the full distance of the beam. So it's going to be 10 times 8 minus 8 times 6 minus 6 times 4 minus 4 times 2. This should equal 0. Let the calculator prove it. Do this in the meantime. Don't forget to put in the units. I just realized I didn't do there. Let's see what this is. Brackets 10 times 8 minus 8 times 6, because that's a force going downwards, counterclockwise, making the beam go counterclockwise. Another one, brackets 6 times 4. This is where most of the mistakes are made, where you start putting in by mistake the wrong distances from where that pivot point is, from where that is. Minus 4 times 2. Open brackets 4 times 2, 0. And there we have it. Here's my shear force and bending moment diagram for this simply supported beam with 3 linear forces, or 3 point loads, or 3 normal loads, vertical loads pointing down onto this beam. And that's it. I hope this is clear and hope it makes sense. Yeah, I hope you guys work well in the rest of the questions that you do.